The probability and statistics project had created a lot of automation in the probability and statistics computations by providing the high-level solvers and a big collection of parametric distributions, and on top of that a library to construct your own parametric and non-parametric distributions by the use of so-called derived distributions. That means you can do functional transformations, you can do parametric mixtures or some other transformations. Also, all of these parametric distributions would support estimation, random number generation, so can be used in the calculations in finance as you see it necessary. Now, it also, as was certainly mentioned in a lot of talks today, that there are economics concepts added to Mathematica version 8, which should again enhance the automation and make your piece of code more expressive of the ideas and not so much the code. Now, the synergy example of that being possible is due to Stas-Chandler, and the idea there is, we are computing the calculations of a premium of death benefit. So in here, a death occurs at a time t, and presumably the payout is $1, and this time t is random, occur and follows the Gompertz-Makeham distribution. So using the time value, the thing is, we can compute, the present value of that payout occurring at time t under the continuously compound interest rate, and we get an answer out of this, and that's a average present value. And then we say, well, suppose that the person is paying a premium continuously, and what that premium should be in order to recover the payout, and we get a formula. So this formula, I'm told, is a classic, but not is the amount of code which took to write it is very small and very expressive. So it shows the automation in effect. Now, coming back to what I'm going to be talking about is that I was involved in implementing more specialized distributions, in particular stable distributions and hyperbolic distributions, and I'm going to be talking about the inners of that implementation. Stable distribution is a family which is closed under the addition. So it's basically the same thing as normal is part of a stable family, normal distribution. And for normal distribution, you know that any linear combination of two normal random variates is again a normal random variate. And in the stable is just a bigger family which satisfies this property, and the functional equation for a characteristic function from a stable distribution is that the product of these two is giving you a characteristic function from a stable family up to a shift. So now the solution to this functional equation would be a function written schematically in front of you, so that's an exponential of something, and it has 4 parameters to it. So this first parameter, alpha, is a parameter which is called an index of stability, and this other parameter here is related to how skewed the distribution is. Now, there are many possible parameterizations in the stable distribution, but and that the possibilities, this ambiguity in parameterization has caused the community quite a lot of harm because people couldn't agree on one. So I hope that in Mathematica would implement 2 of such parameterizations which are most commonly used. So the characteristic function encodes these parameterizations, and the logarithm of a characteristic function in the most used parameterization tells you that the logarithm of characteristic function goes like this. The index alpha is that index of stability, and it is related to the way the density function behaves at infinity. Beta tells you how skewed the distribution is. When beta is 0, the distribution is completely symmetric. The parameters here cannot be arbitrary, and the restriction essentially comes from the requirement that the PDF is non-negative. And in order for PDF to be well defined, the alpha has to be positive and should not exceed the value of 2. The beta has to be between -1 and 1, and delta is a scale parameter, so that it has to be positive, and the location parameter mu must be real. For some of these distributions, as I mentioned, there is a closed form expression. So in particular, as I said, normal normal distribution is a special case of it, and the normal distribution corresponds to the alpha index, which is equal to 2. So here, the PDF of that stable corresponds to a normal, and notice that the delta parameter is not exactly the variance in that case. It's a certain constant, a square root of 2 times that scale parameter is a variance. Now, if you would look at that formula in here carefully, you would notice that at alpha equals to 1, it diverges. A tangent of pi half is infinity. And for this reason, the stable distribution, as it was initially parameterized by economics community, is not, it's not too mathematically nice behaved. So people, for this reason, had created a different so-called zero parameterization, and what that does is just subtracts from this tangent which would blow out. It multiplies it by some term which vanishes when alpha approaches to 1. So this way we sort of compensate the infinity as a pole in the tangent with the zero of some other function. Now, you might say that that's something different, but actually, if you multiply this alpha power, you multiply it by by this term here, you will see that this is nothing but a linear function, and so absolute power of t to a power 1 times the sine is just a t. So what we've added by adding this term is something equivalent to this. So the difference between parameterizations is essentially a shift. Now this parameterization, because of that property that 0 multiplies a pole here, is well behaved when alpha approaches 1, and this parameterization called zero parameterization has much nicer analytical properties and allows in particular for nicer tabulation. So if you wanted to save, say, a PDF, and you wanted to compute how PDF behaves as a function of alpha and beta for, say, tabulation, then this parameterization would be a way to go, because it would not have any artifacts. Everything would behave smoothly and nicely. So in here, I'm trying to convince you that when you compute the limit of alpha goes to compute the alpha non-once a generic function, then take its limit, and you will end up with the same value that occurs when you explicitly set alpha to 1. Now, the relationship between these two distributions, as I said, is linear, and that's basically the proof of it in the Mathematica notation. So all we have to do to come from a zero parameterization to one parameterization is to shift the mu. So that means that the index of stability stays the same and the skewness stays the same. And if you always standardize your distribution, then you don't have to worry about the difference. But in order to show you how type 0 and type 1 are kind of, how do you see this singularity in alpha, we will plot a probability density function for alphas a little less than 1 and a little more than 1, and you will see that for type 0, those two plots are virtually indistinguishable, but for type 1, the mode varies quite a lot due to that singularity. In order to get a feel of what the index alpha and the index beta mean, it's nice to look at the asymptotic behavior of the CDF, and you would see that when x becomes large, then the probability sort of falls off as x to power minus alpha, and that's what that alpha index alpha means. And you can think of stable distribution behaving at infinity as Pareto. The Pareto is index alpha. That's what that alpha would mean. Also, the beta index, the skewness index, would essentially determine, the disparity between the left tail and the right tail. So when x is positive and you kind of reach into the far right, the index in here would be 1 plus beta. When you reach into a left, the far left, it will be 1 minus beta. So if beta is 0, then those two tails are the same. But if beta isn't, then they are different. Also, it's important to know that the Pareto behavior will disappear in one left when beta is equal to either plus or minus 1. So if beta is equal to minus 1, then you don't see the Pareto behavior in the far right. Instead, you will see the exponential decay and that what makes the behavior slightly more difficult. Now, the numerical evaluation of a stable distribution does not have any closed form for PDF in most cases, and therefore we have to resort to a numerical procedure to evaluate the density of the PDF, and that involves a couple of techniques. So first of all, the stable distribution, the PDF of a stable distribution, can be expressed through other special functions, in particular a beast called Fox-H function. Now the PDF is a sum of these two Fox-H functions. Now, and being the Fox-H function, it allows for a certain series representation when the argument is either too small or too large, and I'm just showing here that, you know, when you are in that regime, evaluation of PDF is very quick. You can see that here. But when, you know, you can also use that Fox-H function representation to compute an asymptotic series, and again here an evaluation is quite quick. However, when you are in the intermediate stage, then the obvious idea to try to do is to invert a Fourier transform, but those calculations are kind of tough to do. So the major vehicle for computing numerical values for PDF is the so-called Zolotarev representation, and that's what is used under the hood. I'm not showing you the formula because it will, you know, it's not so important. If you want to know it, I can give it to you, but the point to show is the numerical evaluation here will be slightly slower if you want to compute, because the value of PDF is computed through the n-integrate, and the function that is integrated sometimes can be very sharply picked, and that poses an additional complications. In here, I'm just showing that when you do the inverse Fourier transform, you can end up with the same value, and that kind of just reinforces. So you can do you can visualize the stable distribution because it behaves as every other distribution despite not having the closed form for PDF, and that's how this density changes when you modify the skewness parameter. The stable distribution is used, or it was used, in a finance community in order to try to estimate the log returns of the various indices. So in particular, we will try to here to retrieve a value of SP500, then grab the values since 2009, daily values, the closing values, compute the logarithm of them and the difference, and try to estimate. And the estimation is actually pretty quick, and you get the value. Now from here, you can try to compute the value at risk of what would happen at the 5% level, and compute the associated loss at that level. You can then go ahead and try to use a stable distribution with this value to compute the expected shortfall and the associated risk with that. And because the distribution has heavy tails, so it behaves like Pareto with the index 1.6, the expected shortfall is actually a bigger value in absolute values than the value at risk. And that illustrates the use of long tail distributions to model the log returns to capture the hidden risks of the market. Now the simulation, the stable distribution is very quick to simulate because it uses the mentioned already Zolotarev representation. And the Zolotarev representation essentially tells you that in order to build a random variate, stable random variate, all you'd have to do is to take two uniforms and apply a particular transformation to get them. That's what Mathematica does. So a million of random variates from stable distribution is computed in half a second, and then you can show that the random number generated indeed fall under the curve of the stable distribution. So what's done here is that we take, because a stable distribution is fat-tailed, then if you compute a random variates, lots of these random variates become very big. So in order to visualize it, you had to cut it into a particular window, so effectively showing only truncated distribution. So that's what's done with a histogram. You take the sample, but only show points which go from low to high. And in a PDF, in order to renormalize the distribution correctly, we use truncated distribution, and as you see, the fit is good. Now, I would like to sort of go into the meat of the estimation, because the estimation for this distribution is hard. And the reason it's hard, because the PDF itself is not known in closed form. So from the 60s, when Mandelbrot was advocating the use of stable distributions to model log returns, people started to ask, and how would we estimate it? And the method of moments, something which was common at that time, would not be applicable here because the distribution is fat tail, and therefore for most of the parameters it doesn't have finite moments. So in particular, in here I'm showing the cumulant, and it tells you that the first moment, the mean, only exists when alpha is greater than 1, right? And the second moment only exists when alpha is exactly equal to 1. But also when alpha is exactly equal to 1, all of the higher moments exist. So you end up basically having a distribution which only has mean. And well, if you think about it, the application in financial market only makes sense when alpha indeed is greater to 1, because in order to price an option, you need to have a mean. Otherwise, you can't compute the value of the option. So therefore, stable distribution for alpha in between 1 and 2 is what is used in economics to price it. Now, the technique proposed back in '60 was due to Fama, who noticed that certain quantile ratios exhibit a strong dependence with respect to parameters of stable distribution. Namely, if you compute the ratio of this q at 0.95 minus 0.05 over the interquantile range, then this exhibits a very strong dependence on alpha and hardly depends on beta, and likewise has no dependence of mu and delta. And therefore he said that if we tabulate this, in his paper he tabulated a couple of values of these functions. If you use a tabulated value, you can sort of take your data from your log returns, compute these quantiles, compute the ratios, and from there determine alpha and beta approximately. So this is we've implemented this as one of the routines, but because for certain reasons this is not exposed in the estimated distribution as a method of quantiles, in part because it's not immediately obvious how to implement this method in general. But for stable, if you need to do that, it's available in the statistics library context. So here we generated 10,000 points, and notice that the alpha index is actually less than 1, right? So this is a kind of distribution which is not useful in finance. The estimation actually gets this pretty well. Now it works by recording these fractions of quantiles. We pre-compute the values of this, how they depend on the parameters, store this as the interpolating functions, and then solve for certain values. So these interpolating functions extend as low as alpha 0.08. There is a different method which was used in the literature to estimate parameters, and that would be the method of characteristic function. So the method of characteristic function works because you can take your data, and from that data you can compute a sample characteristic function, and it will be a nice curve which looks like that of a stable distribution, and you could try to fit the stable distribution characteristic function to the sample one. So in order to do that, you'd notice that a characteristic function at, say, type 0, when you compute it at a value when t is equal to 1 over sigma, it looks particularly simple. And in particular, the absolute value of it is just 1 over e. So that means that if you take your data in a computer characteristic function, and if you find a root such that the absolute value of characteristic function is 1 over e, you could hope that that root is 1 over sigma. So this way you can quite reliably find the scale of your distribution. Then the next thing you do is you can look at the phase of it, determine the mu. That's this. And then in order to find alpha and beta, you would essentially compute the characteristic functions at a couple of values of t and do a regression. So this is implemented inside as a stable estimation characteristic function, and it also is pretty quick. What I wanted to show is an application of the application example in the documentation, which just shows this same technique done slightly differently, but in quite an educational manner. So in here, we generate random numbers from stable distribution, compute the sample characteristic function, and just plot the sample characteristic function and the expected characteristic function, you see quite a good agreement. Now, we just pick a couple of values of t for which we want them to agree exactly and solve for alpha, beta, and other parameters of it. And you see that it actually agrees with the maximum likelihood method quite well. Now, the method of maximum likelihood is the most robust and thought out method, and in order to implement it, you need a fast PDF. In order to get the PDF that the Mathematica has is reliable, but it's not fast because it uses n integrate. So the only way out of this would be to use, this shows that it's actually not fast. For 1,000 points, it takes 2.5 seconds to compute the log likelihood. And if you need to do this thousands of times to find your parameters, it's going to be very slow. So in order to overcome this, we use a tabulation and a zero parameterization, which depends on the parameters smoothly. And this tabulation is actually a lot faster. And as you see, it's actually pretty accurate. So those two numbers agree. And this tabulation is what is used to make the estimation work. The stable distribution, as I said, changes the nature when beta becomes plus or minus 1. You see that when beta is in here is equal to like 0.95 or 0.9, the distributions have a power tail behavior here and there. But as soon as beta hits 1, it dives deep down. And that makes the tabulation quite difficult because you have to tabulate both in alpha space, beta space, and X space, and because of that beta 1 being so singular, when you do the interpolation, it starts oscillating too much because interpolation essentially is an interpolation by a polynomial, and in here the nature of a function changes. So the way out is to essentially not interpolate for beta equal to 1, but interpolate up until beta, say, 0.99999, and then try to use asymptotics from that small point down to 1. And that's what we try to do. The tabulated data extend only when alpha goes to 0.5. This is not an issue for financial community because, as I said, the stable distribution is only of interest when alpha is greater than 1. However, for whatever reason you need you need alpha less than 1, then we just resort to Zolotarev representation, and that's why it's slower. In order to get you an idea of why alpha when alpha is less than 0.5, what happens is that the distribution starts being sharply picked. This is a logarithmic plot, and it tells you that when alpha becomes smaller and smaller, then the peak of a distribution grows, even on the logarithmic scale quite high, and the width of a distribution becomes very small. So tabulation of it becomes very difficult. But one of the reasons why I was showing you these inner functions like stable estimation quantile, stable estimation characteristic function, is that when you need estimation when alpha is less than 0.5 and you need it quick, those are the methods to try to use. And those methods are actually also quite good and quite reliable. Now, in order to just quickly tell you how the stable estimation works, we use these methods of quantile and characteristic function to seed the initial value. That's we run the quantile and we run the characteristic function estimation. We get a value, we compute log likelihoods for them. We pick the one with a better log likelihood, and then we use the unconstrained optimization in order to try to find the good value. So this gives a pretty quick and pretty accurate code. So in here we are taking the Dow Jones Industrial Average Index since 2000, and this has close to 3,000 data points. So an estimation now based on data will show you what's happening. You see that the search was being done, and you also saw, if you had a chance to capture that, the value of ABC, which will run on the screen, were different than the one output in here. And the reason that that was happening is because we were doing certain functional transformations under hood to get rid of constraints, that alpha is in between 0 and 2 and so on. And that that allowed us to run an unconstrained optimization which produced the speed. Attempt to do a constraint optimization would actually drop the speed probably by a factor of 10 to 15. The obtained value, has a log likelihood, but notice how long it will take to compute a log likelihood, because a log likelihood will be computed using the Zolotarev representation for PDF, so it takes a while. And the stable log likelihood, which uses an interpolating function, is computed a lot faster. Now this will just show how the data correspond to a fitted distribution, and you would see that it fits relatively well. The hyperbolic distribution is a model which was used in which is used in economics, and it corresponds to so-called mean variance mixture. You start with a normal distribution, and you would consider a mean and a variance of it being a random correlated random variance, and that variate is from the inverse Gaussian distribution. So I find it necessary to give to first say what the inverse Gaussian distribution is. So this is a distribution with the following PDF. Now the catch about it is that literature contains two different parameterizations to it. The one which is chosen in Mathematica you'd see, is a bit asymmetric. The one which is more often seen in the literature, at least the recent literature, is obtained from it by reparameterization. And the reason that people use this one is because you see the parameters chi and psi here control separately the linear and the reciprocal terms in the exponent. So in particular, you can consider a limit of chi goes to 0, and in that case you would recover the inverse gamma distribution, or you can consider a limit of psi goes to 0, and in that case you would just recover a gamma distribution. So the inverse Gaussian in this parameterization could be considered like an interpolating functions between the inverse gamma and a gamma distribution. Notice that for the estimation code in particular, the nasty normalization factor, which involves a Bessel K function, just doesn't allow for very quickly to quickly find the estimates for the parameters using maximum log likelihood. So the mean and variance mean variance mixture in details means that you take a random variate from a standard normal distribution, you multiply it by a square root of u to get to get variance, and you add to it a constant shift, and that variable u is from the inverse Gaussian distribution. So simulation is essentially relies on the on that transformed distribution which I told you. You generate a normal variate, and we generate a variate from the inverse Gaussian distribution, and the generation is performed by using acceptance rejection method by essentially trying to measurize the inverse Gaussian distribution by piecewise exponentials. So these are piecewise exponentials from which we know how to generate random numbers well, and this is how we get random numbers of hyperbolic. And those are actually pretty fast. You can see that the PDF is also in agreement with that. So the difficulty of the estimation is the presence of lots of Bessel K's in there. And in order to overcome that, you'd notice that you'd have to remember that the Bessel K becomes a very simple function when its index is half integer. Because in that case, it becomes a rational function times an exponential. And so the clue was to try to say, well, suppose lambda is a fixed integer, and solve a simpler problem. Suppose lambda is fixed, and it's fixed at half integer. The moment becomes simpler, and we can try to solve the problem by, say, using at least method of moments. So when lambda is equal to -1/2, the moments are simple, and you can just try to solve the algebraic equation to equate the moments to a sample moments, and that could give you an estimation for like lambda equal to half or -1/2. Now, when lambda is not that simple half integer, then the best method that I found was to try to minimize the sum of squares of differences between a sample moment and the formulary moment. And this allows for quite quick and relatively accurate estimation, assuming that you know that lambda is a fixed half an integer. For fixed lambda, when a lambda is fixed, also the equations which determine the maximum of a log likelihood can be computed, and also you'd notice that all of these equations depend on a Bessel K with lambda plus 1 divided over Bessel k of lambda. In here, it's lambda minus 1/2 and lambda minus 3/2. So the ratios of Bessel show up in the equations, and these ratios actually allow for a relatively accurate calculations, which can be done faster than evaluation of Bessel k's themselves. So therefore, in order to make this work, we had to introduce an internal function called Bessel k ratio, and that Bessel k ratio coincides with that. With the ratio we want to compute, but this Bessel k ratio can be computed using continued fraction expansion from a book, and that is done quite fast. So in particular, you generate some random numbers, and that's a Bessel k ratio. It's computed quickly, and using the Bessel k's themselves is longer. So the Bessel k ratio is also closed under the differentiation, and that allowed for those equations which determine the maximum to compute their second derivative, and that therefore for the log likelihood we had a gradient which corresponded to derivatives, and the mixed derivatives corresponded to Hessian. That sped up the finding of the maximum quite a bit. But we are still facing the problem of what are the initial points. So the initial points were obtained by attempting to do this. This actually turned out to be a pretty good method to find the initial points, and from there on, using the Hessian and the gradient with the use of Bessel k's is what is behind the computation of the estimation with a fixed lambda. So you'd notice that in here I would generate a random numbers from a hyperbolic distribution with a lambda being 2/3, and I would try to compute it at 2/3. It will take some 5 seconds because the Bessel case at 2/3 is not too quick. But if you would restrict yourself to lambdas being 1/2, then the estimation is done pretty speedily. So one thing which I thought would be cool to try to do is to try to estimate, suppose you don't know what lambda is. You would try to estimate it for several half integers, and then try to determine for which lambda you'd have a pick. So in here, that's what I'm trying to do right now, and you'd see that for some lambda somewhere close to this range, minus 1/2, you get the maximum, and that's where I should try to look for my lambda. So the general estimation, the estimation of all 5 parameters, is done by trying to retreat the footsteps of what we did right there. We would try to minimize the difference between moments in order to find a good initial approximation to lambda. Then, unfortunately, attempts to compute the gradient in a lambda direction of a log likelihood wouldn't work too well because it involves a new transcendent, which is derivative of Bessel function with respect to lambda divided over the logarithmic derivative of Bessel k with respect to lambda. And this does not admit any quick way to evaluate it. So just showing that this is what is happening. We are trying to take the data, say data which is about 1,500 data points. We're trying to compute the initial approximation to lambda, and I wouldn't wait for this to finish, but I will just show you what's happening when you try to trace the changes. So the initial point is we are trying to do a certain search for lambda. We are trying to find it for lambda 1, lambda 2, lambda 3, and for those lambda try to compute alpha and betas. Then in doing that, we find some messages, but those messages are harmless. And we'll find that lambda, and then around it, we will try to minimize the function, which is a log likelihood of the estimated distribution for fixed lambda. Think of it this way. For a fixed lambda, denote the value of log likelihood for a fixed lambda, a certain function of lambda, and we are trying to maximize it. Just similar to what I was trying to do here. So for each fixed lambda, we will find the estimated distribution, compute the log likelihood, and that's what we are feeding inside find maximum. And it will take a long while to do that because the Bessel case functions are not too fast to compute. So presumably, when in the next sub-release we'll make Bessel k functions faster, this method will actually also become quite faster. So I ran these calculations, and I ended up with the answer in about 10 minutes. I was just saying that, we will get a value, we'll compute a log likelihood value of it, we got this. And then I said, what if instead I just gave it a lambda, and say in that case I was giving a lambda of minus 0.2, it will find me the answer quite a lot faster. So also notice that the value of log likelihood for that answer is virtually indistinguishable. If you will take that instead of minus 0.2, you will take 0. It will also find you the values. The alpha and beta parameters will be quite a lot different, but the value of log likelihood will be a slightly bit smaller. And what that means is what I once read in the article, that in the lambda direction, the minimum is very shallow. So that means that the precise value of lambda really doesn't matter when you try to estimate it, because the value of lambda modifies very slightly the behavior at the far end of the distribution. So hopefully, by exposing you to this inner internals of the distribution, you can make your estimation quite a lot faster at the expense of cutting the corners in some places where it's less important. Okay, thank you. Thanks.